right, testing to see if transcription okay. All right, welcome everybody. So before I start today's lecture, the final exam schedule has been released. So as of right now, our final exam is set for April 25th. It'll be similar in format to the midterm exam. Of course, it'll cover the entire material all through the whole term, but the format and the timing will be similar in that you'll have all day Friday, April 25th to do the exam. And I'll also put a practice exam for you guys up later on. But I'll give more details on the final exam going forward. Just know that for now, it is set for April 25th, Friday, April 25th. Okay, so today we're going to be looking at ANOVA, but I also want to first touch on a little bit how to understand to select the appropriate inferential test. Right? What are the criteria that you should follow in order to know what of the many tests that we've already looked at and we'll look at further on in the course, which one to choose. So we can look at it in terms of this table here, where we have on the upper in the columns, we have our different samples, right, our data. And then along the left, we have the type of data that we're dealing with. Remember our different data types, nominal, ordinal, or continuous. So the first thing you can do is look at this table to have an idea. And you can see within each of those squares, we have a whole bunch of tests, some of which we've done, some of which we will be doing in the near future. So what is the first criteria I should be looking at? Well, it depends on how many samples you have. We've already looked at the one sample means test. We've also looked at the independent t-test using two samples. Also t-test for paired or dependent samples. And then we've also looked at, and we're going to look at today, we're going to look at how to analyze 3 or more samples for differences using ANOVA. Right, so that's one criteria, right? How many samples are we dealing with? 1, 2 which are paired, 2 which are independent, or are we dealing with 3 or more? And of course, what type of data is our measurements taken in? Is it nominal, ordinal, or continuous? That's our second main factor. But based on those two criteria, we can use this table or this matrix to help us identify which statistical test we might want to run. Another main criteria, the third one, is does our data follow a parametric or a distribution? Is it normally distributed, and therefore we can do a parametric test, or is it non-normally distributed? Therefore, we'd have to do a non-parametric test. That's why we're looking at all those Shapiro-Wilk and other types of tests for normality in the labs. It's to determine whether our data that we have is normally distributed or parametric or not, because that'll determine what type of test we're going to do. So parametric stats, right, and what they are is that they're based on a bunch of assumptions basically about the distribution of which our sample is taken. Now, a main assumption for a parametric test is normalcy, right? Our data is following a normal distribution, but there are other assumptions that will determine whether our data that we have is parametric or non-parametric. So basically, when we have parametric data, we can run one set of tests. But if our data is not parametric, it's non-parametric, we have to run a different version of that same test. Right, so we've looked at here on if you had paired data, right, and it's continuous data. If your data is parametric, you could run the matched pairs t-test for difference. But if your data does not follow, say, a normal distribution and therefore is non-parametric, right, you would better be suited to go with the Wilcoxon sign rank test for non-parametric data. If you have two samples and you're looking to see whether they're independent from one another or not, if you're parametric, you can do the independent sample t-test. If your data is non-parametric, you have to go with the Mann-Whitney Wilcoxon rank sum, which we're looking at later on in a couple lectures here. And then if you have 3 or more samples, if your data is parametric, you can go with ANOVA, analysis of variance. And if it's non-parametric, you have to revert to a non-parametric. In this case, it's going to be one of the options is the Kruskal-Wallis analysis of variance, where you rank the data. Right, so non-parametric stats is basically a statistical method in which the data, usually the main criteria is that it does not fit a normal distribution. Right, so if we have normally distributed data, say we run an empirical look test, and then we find that our data is normally distributed, we can do our parametric test depending on what type of test we want to do, whether that be a t-test or a correlation or analysis of variation in ANOVA. But if we find maybe it's very skewed or kurtosis is off for our data, does not align to a normal distribution, and our empirical test tells us that it's to reject the hypothesis that it is normally distributed, we'd have to go with a non-parametric version, whether it be the Mann-Whitney or the Spearman rank regression coefficient. Right, so for every parametric test, we have a paired, at least one paired non-parametric equivalent that we can go with if we find out that our data is not parametric, right? So the paired t-test, if our data is not parametric, we can go with the Wilcox and rank sum, right? Unpaired t-test, Mann-Whitney u-test. We'll look at that correlation in our data. If our data is parametric, we go for Pearson correlation. If not, we have to go for Spearman. And then if we have 3 or more samples and we're looking for whether one of those samples is different or not, we can go with the one-way analysis of variance, ANOVA. If not, we can go with the non-parametric version, which is the Kruskal-Wallis test. Right, so things to keep in mind when trying to figure out what is the appropriate test to select. First of all, what is your question, right? What are you trying to find out? Is it something of difference, right? Is the temperature different between 2 locations, or the height's different in 2 groups of people? So if you're looking to determine whether there's a difference between 2 or 3 or more groups, right? Depending on how many samples you're looking at, you can go with t-test, difference of means test, ANOVA, chi-squared, which we haven't looked at yet, but we will. Or if it's non-parametric, you can go with the Kruskal-Wallis. If you're maybe trying to figure out what's the strength of a relationship between variables, maybe you're looking at the variable of temperature and the variable of CO2 emissions. You want to see what kind of relation you have between them. Maybe you want to do a correlation analysis to see how much there is an association, or you can do a chi-squared. Again, we'll get into the chi-squared in a couple lectures. And then if you wanted to see a little bit more, if you wanted to see more, if there's something more than that, just an association, say between CO2 and temperature, you could run a regression analysis. So you can see more and have more of an idea of the exact nature of the relationship between CO2 and temperature. And regression, like correlation, is something that we get into this week as well. Right, so again, another criteria is how many samples are you dealing with and what kind of samples do I have? What's the type of data, right? Nominal, ordinal, continuous was my question. So these are kind of like the 4 summary points that you should have in your mind if you're trying to figure out which statistical test you want to go with. All right, so with that out of the way, let's get into ANOVA. So ANOVA is what we'll be doing in Lab 5, this week's lab, and it stands for Analysis of Variance. So it's a stat tool that's designed to determine whether you have at least one, when you have 3 or more samples or groups. You can use ANOVA if your data is found to be parametric. You can use ANOVA to determine whether one of those groups, like the mean of one of those groups, significantly differs from the means of the other groups, all of your data sets. Or are those differences that you do see just random and not significant? So this is what we can use ANOVA for. And again, the main criteria, if you have 2 groups and you want to see if they're different or independent from one another, you can use a student t-test. But when you have 2 or more groups, you cannot no longer use a student t-test. You have to go with the ANOVA. Okay. So if we're only examining the relationship between two, say, categorical variables, nominal variables, we could use, instead of ANOVA, we could use a chi-square test of independence. So if we're not dealing with continuous data and we're instead dealing with nominal data, we can use a chi-square test of independence. Again, we'll get into the chi-squared later on. So here's kind of the summary of a one-way ANOVA. Right, so one-way ANOVA is a ANOVA test where we're looking at just one variable across 3 or more different samples. The type of data that we're dealing with is continuous, right? It's a parametric test, so it has to follow certain assumptions like normality. And the way that we interpret it is that we do the analysis like we've done with the other test, like the t-test. We set a certain confidence value, whether that be 90 or 95%, and then we run the test, and then based on the results, we determine whether we're going to fail to reject or reject the null hypothesis. So what does the ANOVA give us? Well, the ANOVA essentially produces a stat called the F-stat. So what the F-stat is, essentially you can think of it as a ratio of the variance between the groups relative to the variance within the groups. So the F-stat gets larger as the variance or difference between the groups gets larger compared to the variance within each individual group. So when you have a low F-stat, that means that there's more of a likely chance that there's not a significant difference between your different groups, that the differences that you do see are just due to random sampling error. Okay. So essentially what we're doing, we're calculating the F-stat. We're essentially assessing the between group variability or differences relative to the within group variability. So this is how the F-stat is calculated here. Don't worry too much about it, but essentially it has to do with the number of groups and the mean between each of those groups. So basically with the F-stat, right? So you can compare two F-stats here. We get a low F-stat like we have on the left here. That means we have a lot of overlap between our different samples. Okay? Means that the variance within each of the samples itself is relatively large compared to the variance between the groups. When, like on the right, where we have a high F-stat, that means that the difference between the groups is relatively high compared to the variance or difference within each of those samples or groups. That's how to interpret the F-stat when dealing with ANOVA. So with ANOVA, we can look at various numbers of variables. So if we're just looking at one continuous variable, we can run what's known as a one-way analysis of variance. But if we can look at not just one variable, we can look at 2 or more variables. So if we look at 2 continuous variables across 3 or more groups, that's going to be called a two-way ANOVA. So what's the working hypothesis for the ANOVA? Well, they're all, doesn't matter whether it's a 1 or 2-way ANOVA. The null hypothesis is that there is no difference between the means of the different groups, that the differences that we see are just due to random sampling error. And when we reject that null hypothesis, that means that we're going to assume or assert that there is a significant differences in at least one of the means of those groups. Right, so here's just a summary of the differences between the one-way, two-way, and three-way ANOVA. So a one-way ANOVA is just looking at a single factor or variable across 3 or more groups. Two-way is looking at 2 variables, and three-way is looking at 3 variables across those groups. So that's the difference between a 1, 2, and 3-way ANOVA. So what are the, because ANOVA is a parametric test, we have to have some assumptions before we can properly use ANOVA. So ANOVA not only assumes normality in our data, but it also assumes something called homoscedasticity. And basically that word means that the variance between your different groups is essentially the same. So as we'll see in the lab, to do a test for, sometimes this homoscedasticity is also referred to as the homogeneity of variances. Basically, we're testing to see whether the variances or the spread of our data values is the same between all of our groups. To test this, we can do something called the Levine's test, which is just another stat test, which tells us whether we have similar variances or not between our different groups. right? So what is homoscedasticity? Well, essentially, it tells us whether the scatter in our data is somewhere between our groups or not. So at the top there, we can see that we have homoscedasticity, meaning that we have relatively consistent variance of our data. At the bottom, we have heteroscedasticity, which tells us, that indicates that we have a difference in the amount of spread in our data between our different groups. So some more conditions or assumptions that we need to fulfill for ANOVA are is that our samples are independent from one another, right? There's no overlap of the data between them. Same variance, right? Homoscedasticity. And then that the populations are adequately normally distributed. When we violate one or more of these laws, typically you cannot adequately use an ANOVA test, and you have to go with the non-parametric version. And one of the main non-parametric versions of ANOVA is Kruskal-Wallis test. So summary here, the Kruskal-Wallis, right? Same as the ANOVA in that we're looking at 3 or more groups, right? But in this case, we take our continuous data variable, right? And it's a non-parametric. So it can be continuous data or ordinal data, where a data is ranked. The key thing here is that it's a non-parametric test. So when we're looking at a two-way ANOVA, right? It's a parametric test when it's continuous data, that we have more than one variable of interest. So let's do an example here. So imagine we have a sample, and we have a sample of clutch size of different egg robin nests in Kelowna, Vernon, and Salmon Arm. So we've gone out to 9 nests in these Kelowna, Vernon, and Salmon Arm and counted how many eggs are in each of these nests. So there's our survey right there for the 9 nests seen in Kelowna, Vernon, and Salmon Arm. So we have 3 samples or groups. So we cannot do a t-test because we can only do up to 2. Right? Only use 2 in an independent samples t-test. We have 3 groups. So we can run a one-way ANOVA because we're only looking at one variable, which in this case is a number of eggs, aka clutch size in this case. So let's first, following our steps in our formal statistical test, right? Let's formulate our null hypothesis. So our null hypothesis is that the means of the clutch sizes in Vernon, Salmon Arm, and Kelowna are equal, that the differences that we see are trivial and not significant. And the null hypothesis for each one in this case is that at least of the one of the means, one of the groups has a mean which is significantly different than the other 2. So we can also use the ANOVA in Excel, again, using the data analysis tab there under data. So there we have ANOVA single factor, hit OK. Enter your data into the input range, right? Making sure that Excel knows that your data is grouped by columns, not by rows. I'm going to enter an alpha value of 0.05 for my test. And then I'm just at the output options. I'm just telling it what cell to input the results table. So here's the Excel spreadsheet itself. There's my data, the different locations. Yeah, I'm going to go to the data tab with my data analysis. I'm going to go find ANOVA at the top, single factor. I'm only looking at one variable between those 3 groups. I hit OK. And then it's going to ask me in its window to enter my data. So I'm going to hit the up arrow there. And I'm going to drag over top of all of my data. Notice that I kept the labels in there, so I'm going to make sure I have a checkbox on for labels. And then I'm going to tell it to output in that cell right there. Okay, once I'm done that, I hit OK. And there's my results for the ANOVA analysis. So how to interpret this? Well, let's look at the F-stat. Remember, the F-stat tells us the amount of variance between the groups relative to the amount of variance within the groups. I can see I have a relatively low F-stat, okay? And the p-value is relatively high. So these are both indications that we're likely going to retain the null hypothesis and that there's no significant differences in the mean clutch sizes between the nested Kelowna, Vernon, and Salmon Arm. And you can see I've actually made some box plots at the bottom there. You can see that the distributions of the number of eggs in the nest between Kelowna, Vernon, and Salmon Arm are relatively simple. So it's not really surprising that my ANOVA test is telling me not to reject the null hypothesis. Okay, so let's imagine we go back the next year, however, and we do another survey and we have another set of data. So now this is our new data set for the number of eggs in 9 nests collected or surveyed in Kelowna, Vernon, and Salmon Arm. And the results from this ANOVA test, right? I see I get a relatively high F value, 75.12, and I have an exceedingly small p-value, 4.66 e to the minus 11. So of course that e to the minus 11 basically means that you're moving your decimal point to the left 11 places. So virtually 0 for a p-value. So both of these are indicating that at least I have one group which has a significantly different mean of eggs compared to the other one. So in this case, I would reject the null hypothesis and therefore assert that at least one of those nests, one of those groups, has a significantly different number of eggs in them compared to the other ones. All right. So that's the end of this video for ANOVA. Again, you'll need to watch this video, or should watch this video before you start lap 5 to give you a little more background. And I'll see you in the next video where we're going to talk about correlation and regression.